Hi, we start with chapter 4 and with section 4.1, which is theory of linear equation. We already have seen linear equations of order 1. So linear equation of order 1, we already learned how to solve them in chapter 2. But now we are going to give the theory. For higher orders, there's no method that solves all linear equation. In fact, you would see that we only solve linear equation in very specific cases. Okay? But we'll introduce now the theory of linear equation and in section 4.1, and in the rest of the chapter, we are going to deal with specific examples. Let's define definition. Let's define a linear operator. So an operator is a map on function that assigns to each function y, so an operator L, another function L of y. Now if L of y depends on y and its derivative, we say that L of y is a differential operator. Okay, so this is the definition of is a differential operator. Well, let's give an example. Let's say L of y equal y prime. So this takes a function y and gives me the derivative. So in this case, for example, what is L of sine x? So this gives me L of sine x is the function cosine x. L of the function e to the x is the function e to the x. Well, another example is L of y equal y squared plus 1. In this case, what is L of e to the x? It is the function e to the 2x plus 1. You can take another example, L of y equal y second minus x y prime. What is L of x in this case? L of x is the double derivative of x, which is 0, minus x times 1, which is equals the function minus x. See? So we can write an ODE. This I said this in chapter 1, but we never really used it. But now in this chapter, you're gonna see that we're gonna use it a lot. In general, we can write an ODE as L of y equal f of x with L a differential operator. Okay. Let's say an example. Let's take, for example, the ODE y second minus x squared y prime plus y squared minus x equal to 0, or plus x equal to 0. So I can write this ODE as everything that depends on y, I keep it on one side. Everything that's independent of y, I bring it to the other side, equal minus x. Then I define the operator, so define L of y equal y second minus x squared y prime plus y squared. So this is a map that takes a function y and gives me the function y second minus x squared y prime plus y squared. I can write the ODE as L of y equal minus x, which means gives me the function y whose image is minus x. This function is the solution to the ODE. Now definition, we say, so given an operator L we say L is linear if and only if L of y1 plus y2 equal two conditions, L of y1 plus L of y2 and L of cy1 equals C L of y1 for all C in R, and in some cases you can say for all C complex numbers. So this means the image of the sum is equal to the sum of the image, and if I multiply the function by a constant, it's like multiplying the image by a constant. An example, so L of y equal y prime is a linear operator. Why? So let's check. So let's see. What is L of y1 plus y2? It is y1 plus y2 prime, and this is equal to y1 prime plus y2 prime. But y1 prime is the image of y1, and y2 prime is the image of y2. Okay? And L of cy1 by definition is cy1 prime, but what is the derivative of a constant times the function? Is cy1 prime, and this is C L of y1. And this implies that L is linear. Both of these. Another example is L of y equal x squared y second plus x y plus xy. So you can check that this is linear again. So what is Ly1 plus y2? This is x squared y1 plus y2 prime plus x times y1 plus y2. And this is equal x squared y1 prime plus x squared y2 prime plus xy1 plus xy2. And this is equal x squared y1 prime, double derivative, x squared y1 second plus xy1, I can write it as such, plus x squared y2 second plus xy2. And this thing is the image of y1, and this thing is the image of y2. So this is checked. What about L of cy1 or L of cy? I use cy1, I use y1 above, so cy1. This is x squared times cy1 double prime plus x cy1. But x squared, what does the derivative of c times y1 is cy1 second plus x times cy1. And this is nothing but c times x squared y1 second plus xy1. And this thing is nothing but the image of y1. So this is checked, and this implies L is linear. Now what about L of y equal y prime? Now this is not linear because we can see that what is L of 2y, for example? L of 2y is 2y times 2y prime times 2y prime. And this is equal 4y prime, which is different than 2 times L of y. So this is not linear. And similarly, L of y equal y squared is not linear for the same reason as above. Okay? Okay. Now linear ODE of order n are of the form an of x times the nth derivative of y plus an minus 1 of x times the n minus 1 derivative of y plus a1 of x times y prime plus a0 of x times y equal a function of x. So if I bring everything everything that is independent of y to one side and everything else to the other side, I will have yn, the nth derivative multiplied by a function of x only. yn minus 1 is multiplied by a function that depends on x. It cannot depend on y or its derivative. Here where f is continuous function, well, f a continuous function, a0, a1 up to an are continuous, and a sub n is not identically 0, which means, otherwise it will be of order n minus 1. So in this case, the ODE can be written in the form Ly equal f of x, where L of y equal an of x yn plus a0 of x y, a linear, where L of y is linear operator. You can see that's a linear operator. You can prove it as I proved that the derivative is a linear operator. So an example is like y second minus x squared y prime plus 2xy equals sine x squared plus 7x. This is linear equation because I have y second multiplied, this thing is a linear operator, and the right hand side depends on x only. Okay, y second is multiplied by 1, y prime is multiplied by minus x squared, and y is multiplied by 2x. This is fine. However, y prime equal x is not linear, as we saw that this thing here is not a linear equation, because I have y times y prime equal x, and y times y prime is not a linear operator. Y prime here is multiplied by a function that depends on y. Now we have the following. Existence theorem, and uniqueness theorem for linear IVP. So theorem, given the IVP anx, well, given the linear IVP, I have anx nth derivative plus an minus 1 of x yn minus 1 plus a1 of x y prime plus a0 of x y equal to 0, equal to f of x, and I have y at x0 equal y0, y prime at x0 equal y1 up to yn minus 1 at x0 equal y. So I should be given y prime yn minus 1, this is y sub n minus 1. So it should be given n condition at the same point. This is a linear of IVP. Okay. Now notice the condition. If a0, a1 up to an and f are continuous functions in an interval I, in an open interval containing x0, and an of x is different than 0 for all x and I. This is different than the condition here. Here an is not identically 0. It can be 0, it can be 0 at some point, but the important thing is that it's never well, an not identically 0 means it can be any function but 0. It can be a function x, it can be a function x minus 1, although for example the function x minus 1 is equal to 0 at x equal 1. But the function x minus 1 is not identically the function 0. Now here I'm saying that the function an should be different than 0 for all x in I, in the interval I, and the function a0 up to an and f are continuous. Then the IVP has a unique solution. It has a unique solution. Moreover, the solution y is defined for all x in I. So I can know the domain of definition of my solution for all, before solving my equation. This was not the case in the Picard-Lindlof theorem. Picard-Lindlof theorem was about any ODE, for the IVP, first order IVP, not necessarily linear, and it only gave me existence and uniqueness at a neighborhood of x0. And I couldn't know how large is this neighborhood unless I solve the equation. This is telling me that the interval I, where all my coefficients are continuous, and where my leading coefficient is different than 0, then I will definitely have a solution. This solution will be unique, and well, the solution will be unique, and it will be defined for all interval I. So just a remark, in the case where n equal 1, so let's prove it in the case when n equal 1, the IVP is a1xy prime plus a0xy equal f of x, and I have a1 of x different than 0, yes, for the condition. And let's say I have y of x0 equal y0. So this implies that y prime of x equal f of x over a1 of x y minus a0 of x over, no, it's f of x over a1 of x, sorry, minus a0 of x over a1 of x times y. So I have y prime equal a function of xy, where h of xy equal f of x over a1 of x minus a0 of x over a1 of x y. So what is h? H is continuous in, well, h is continuous for all x belongs to I. Why? Because a1 is different than 0, f is continuous, a0 is different, and a1 different, and for all y belongs to R. Remember, h is continuous for x, y, such that x is interval I and y is in R. What about h sub y? H sub y is equal, f of is equal, differentiate this with respect to y, equal minus a0 of x over a1 of x, and this is continuous for all x in I and for all y belongs to R. So this implies that by Picard theorem, the IVP has a unique solution y of x for x in some interval x0 minus delta, x0 plus delta. Just give me in a neighborhood. But the above theorem gives me existence and uniqueness for all x in I. Okay, it gives me a better result in terms of domain of definition. Let's give an example. Let's take y prime over square root of x minus 3 plus log of absolute value 5 minus x times y equal to 0, and y of 4 equal to 2. And the question is, show that the above IVP has a unique solution and find, well, without solving, definitely, the largest interval containing x0 equal to 4 for which we are guaranteed or we are assured that a solution exists and is unique. Well, now notice that, so solution, notice that the ODE is linear. I have a1 of x is equal 1 over square root of x minus 3. This is continuous for x larger than 3. Do you agree? And I have a1 of x, so I need all the coefficients to be continuous. What about a0 of x? a0 of x is log of absolute value 5 minus x. This is continuous for x different than 5. What about f of x in this case? F of x is equal to 0. This is continuous for all x in R. And I have a1 of x, which is equal to 1 over square root of x minus 3, is different than 0 for all x larger than 3. Do you agree? So let's see, what are the bad points then? Okay, I want x larger than 3, let's say this is 0. So I should be looking here. And I want x different than 5, so 5 is a bad point. Okay. And now I need to solve near x equal to 4. This is x0. So what is the largest interval containing 4 for which all these conditions are satisfied? It is the interval I equal 3, 5. In this interval, I have a unique solution. Now let's say example. Let's take the ODE x y prime minus y equal to 0, y of 0 equal to 0. Okay. So notice that here I have a bad point. Okay. So notice that the ODE is linear. I have a1 of x equal x, okay, but for every interval containing x0 equal to 0, so I have for every interval containing x0 equal to 0, this I have a for every interval x0 equal to 0, a sub 1 of x. Okay, I mean, since a sub 1 of 0 equal to 0, okay, that's right. Since a1 of x equal to x, a1 of 0 is equal to 0, so there is no interval, there's no interval containing x0 equals 0 for which, no interval I, for which a1 of x is different than 0 for all x belongs to I. Do you agree? Because at 0, every interval contains 0, and a sub 1 of x equal to 0 equal to 0. Then we cannot use the existence theorem, the existence and uniqueness theorem for linear IVP. Well, does this mean that there's no solution? Definitely not. I mean, because this theorem goes one way. If one of the conditions is not satisfied, it does not mean that you don't have a solution. It does not mean that if you have a solution, it's unique or not. It's that simply you cannot use this theorem. You have no information. However, notice that a function y equals 0 is a solution, and the function, so I have a solution, y equal x squared is also a solution. So these two functions are solution. Y replace, they both satisfy the initial condition, and if you replace y by 0, you get 0 here. If you replace the function y by the function x squared, you get, well, x squared, x times y prime, which means x, okay, no, this is, let's put minus 2y, it doesn't, sorry. So if you take y equal x squared, yes, let's put here 2y. Or just let's not put anything. Let's not change this. So y equal x squared is not really a solution. Y equal x squared over 2 is a solution. Y equal x squared over 2 is a solution. Just replace y by x squared over 2. So if you took y equal x squared over 2, y prime will be equal to x. Okay? And if y prime equal to x, we get x. This is not correct. So let's take y equal ax squared, y prime equal 2ax. Okay, so let's put 2 here. Okay, so if you put y equal x squared, y prime equal to x, yes, so y equal x squared is a solution. Sorry about that. So y equal x squared is also a solution. Notice that y equal ax squared is also a solution. Okay, and you have all these, I mean, you have infinitely many solutions. Notice there's a function y that is like 0 here, and ax squared here is also a solution. So you have infinitely many solutions in this case. But maybe let's give another example. If I take xy prime equal to 0, and I take y of 0 equal to 0. So how many solutions I have in this case? Also here I cannot apply the existence theorem, the existence and uniqueness theorem. But assume there exists a uniqueness theorem, but notice that y equals 0, the function 0 is a solution, but is it unique? In fact, it is unique, but I cannot prove it using the existence and uniqueness theorem. How do I prove it? Assume there exists a solution y in an interval I equal minus delta delta for some delta positive. It should be a solution containing x equal 0. This implies that xy prime is equal to 0 for all x in the interval minus delta 0. Do you agree? And, well, let's say minus delta delta. This means that xy prime equal to 0 for x in minus delta 0. But for x in this interval, x is different than 0. This implies that y prime equal to 0 for x in the interval minus delta 0. and this implies that y is equal to constant c1 for x in minus delta 0. So this means y of x is equal to c1 for x in minus delta 0, but by continuity, the limit as x goes to 0 of y of x should be equal to y of 0. But what is the limit as x goes to 0 of y of x? It is c1, because y of x is a constant, equal y of 0, and y of 0 is equal to 0 by the condition. And this implies that y of x equal to 0 for x in minus delta 0, and similarly y of x is equal to 0 for all x in the interval 0 delta. Do the same thing but on the different interval. This implies that y is equal to 0. So this tells me that if I have a solution for this equation, this means that the solution of this equation is unique. Although I could not use the existence and uniqueness theorem, but I'm trying to tell you here in this example that if the condition of the existence and uniqueness theorem apply, it means I have a unique solution. If they don't apply, many things can happen. I might not have a solution. I might have, well, I didn't do an example where I might have a solution. What I showed you, I might have infinitely many solutions, and here I might not have, and here I show you that I might have a unique solution, and maybe a third example where I don't have a solution. Example, x y prime equal to 1, y of 0 equal to 0, and here no solution, since if a solution exists, it should satisfy the ODE at x equals 0, which means 0 y prime of 0 equal to 1, and this implies 0 equal to 1 contradiction. So anything can happen if the conditions are not satisfied. Oh. And well, I will stop here, okay, for the first part of the lecture.